Assalamualaikum warahmatullahi wabarakatuh. Let me introduce my teams. There are Felix Cahyadi, Bunga Edenia, Mulia Sudiastuti, and then myself, Siti Zaratojana. In here, we would like to talk about our review result for a journal entitled Widespread Subsidence and Carbon Emission Across Southeast Asian Peatlands, written by Elysian and colleagues. In insular Southeast Asia, most peatlands have been converted to industrial plantation, smallholder agriculture, or degraded peat swamp forests. The drainage accompanying this land conversion lowers the water table, exposing peat soil to oxygen, allowing aerobic oxidation and fire, and resulting in carbon dioxide emission and subsidence of the peatland surface. If this subsidence persists by long term, many coastal tropical peatlands that are only a few meters above sea level will experience frequent flooding or complete inundation and salt water intrusion in the coming decades. There are several ways to monitor land subsidence on peatlands, such as use pulse anchored into the underlying clay, and also use interferometric synthetic aperture radar or INSAR remote sensing. The method used pulse anchored into the underlying clay have some weakness, like limited by the low number of poles, the challenges of multi-layering monitoring, and the inaccessibility of field sites. In interferometric synthetic aperture radar or INSAR remote sensing methods, presented by a large-scale, high-resolution assessment of subsidence on tropical peatlands. From that, will be documented the subsidence across all distributed land use categories, including smallholder agriculture, shrubs, ferns, cleared or burnt area, and degraded forests. Over 90% of the peatlands area surveyed is subsiding, demonstrating that subsidence is not limited to plantation.
Okay, moving on to interferometric synthetic aperture radar, or INSER remote sensing of subsidence. So this is an active remote sensing techniques which detects centimeters to millimeter scale change in elevations by measuring phase change in the reflected microwave beam between subsequent flyovers of synthetic aperture radar spacecraft, and subsidence rates are derived by taking the linear fit to the time series of deformation at each pixels. And this approach has been used to quantify volcanic deformations, earthquakes, and interseismic deformations. And we measure subsidence across 100 times 100 kilometers square frames in Indonesia and Malaysia using a correlation-based selection method derived from a small baseline subsets time series approach relying on ELOS IL-band data from 2007 and 2011. And we demonstrate that the correlation based in interferometric synthetic aperture radar time series method applied to L-band data overcomes several obstacles to measuring long-term subsidence in drained tropical peatlands. And then we validate the estimated subsidence rates from ISNAR, time series, and mean velocity maps in several ways. First, we confirm that the subsidence maps show no deformation in peatlands areas and show clear and accurate delineations of the subsiding peat boundaries. And then second, we verify that the spatial discontinuities in subsidence rates correspond to past or present land use boundaries in nearly all cases. And finally, we validate trends in interferometric sensing aperture radar subsidence rates with subsidence pole measurements.
Hello everyone. Now let us head to the next section, which is called the subsidence trends. So Based on the INSTAR measurement data, we can see that widespread land subsidence happens across peatlands in Southeast Asia, and the distribution of the subsidence can be seen in Figure 1. And there, there we have a histogram of mean subsidence rates, and it turns out over 90% of all the peatlands in Southeast Asia are subsiding. And another interesting finding is that the mean subsidence rates across distinct land use categories are comparable. And in Figure 2, we can see um, land use boundaries in the subsidence pattern, and meanwhile in Figure 3, the land subsidence patterns are pretty much invariant. And that might be caused um, by the systematic drainage efforts. And what that means is that different land use does not inherently affect the subsidence directly. Rather, it is the drainage system that causes the land subsidence. And another interesting phenomenon is that the subsidence rates evolve over time. As we can see in Figure 4, the subsidence rates of recently established plantations are higher than the old one. And the reason for that might lie in the change of pit properties, decrease in drainage depths, and full decomposition.
Okay, my name is Mulia. I want to explain about upscaling subsidence to carbon loss. The subsidence measurements, when combined with bulk density data, integrate carbon loss over time and capture all carbon flux from the pit, including, for example, fluvial carbon export. The increase in subsidence measurement from hundreds of poles to hundreds of thousands of INSAR measurements enable us to extrapolate subsidence value and corresponding carbon dioxide emission across insular Southeast Asia on the basis of extensive spatial coverage. And so, to upscale this measurement across the region beyond the 8 INSAR frames, while still accounting for difference in regional land use distribution, we use a regressions tree approach based on classification of present land use at the time of the subsidence measurements, and the second is distance from the pit age, and the last is the past land use in the 90s as a proxy for time science drainage. And we can estimate regional carbon dioxide emissions due to pit oxidation. We multiply the subsidence rate by the pit bulk density and carbon content, following method of the Kornberg and Heuiger, and using values and uncertainty range for pit properties from the literature. And the conclusion in this research, we find that the drainage of tropical peatlands in insular Southeast Asia result in net carbon loss. In 2015, confirming that the long-term pit oxidation is a large source of carbon dioxide emissions consistent with a previous regional